Now it's difficult to.
All right, let's go ahead and get started. Welcome, welcome. So, how's the project coming? Has anyone started the project? What project? Yeah, you started? Yeah? Halfway done? No?
The command line interface is completely done.
Nice. That's good. That's good. You guys got started? Yeah? You don't seem very happy about that. We got it started. That's good. At least two groups. Yeah, good. No one else? So who's planning to use Python for the project? Nice. That's good. How many of you will be using Python for the first time for this project? Hey, nice. All right. Well, good luck. Let me know if you run into problems. Better yet, let Piazza know if you have problems. Okay. So my TAs wanted to thank you for putting in your names correctly last time. That made a big difference for them entering all the attendance for last time. So if you weren't here, ASU email, full name, makes the TA's job a lot easier. So thank you for that. Okay, let's review some things from last time. Why does authentication need to be done concurrently with acquisition? Yes?
And it has to do with protecting the integrity of data.
Has something to do with it? Yes, authentication does have something to do with protecting, but why do we have to do it concurrently with acquisition? Yeah?
I'm sure that we don't invert the original data.
Yes. Go a little bit further. Just give me a little more detail. Because what you said is basically what he said, almost. A little bit different. We need to make sure that we don't inadvertently change the data when. As we're acquiring it. Yes, very good. Okay, next. Why do we need acquisition as part of the forensic process? Why do we even need it? Why is it part of the process?
Have a copy of the data to analyze.
Yeah. Why? But why do we need a copy?
Because you have to be very careful not to modify the actual evidence, because that, for example, in like a court of law, it can be very easy to argue that we manipulated the evidence in some way. We're working on the actual evidence and change something.
Yes, exactly. So what he said was that we work on a copy instead of the original, just to make sure that in case something happens while we're analyzing evidence, we can always go back to the original and either make another copy or whatever it might be. But we have that layer of protection between what we're doing and the analysis. Okay. What is a hash function? What's a hash function? Yes.
It takes continuous input and maps it to a discrete mapping, and it ideally should change if you change the data.
Yes, very good. So you can give it as much data as you want to, infinite input space, but a fixed size output space. And that is really helpful because if we have infinite versus fixed, we're obviously going smaller, right? And that could be really helpful for a lot of different cryptographic reasons, many of which we don't care too much about in this class. It's just not the focus. But what is the purpose of hash functions with respect to forensics?
So when you're doing acquisition, you can hash the original copy of the data, and then you can hash your copy, and then if they are the same, then you know that you haven't modified the data.
Right. Yeah, very good. Okay. What are some of the desirable characteristics of a hash function? Do you use any hash function for forensic purposes? Yeah.
should be able to compute it quickly.
Yes, we should be able to compute it easily and somewhat efficiently. Yes. What else? Yes.
Shouldn't be like backwards compute.
Yes, we should not be able to derive the input from just the output. Very good. Yes.
You should not be able to find instances of data that stays in hash.
Yes. And so for the purposes of this class, we're not going to distinguish between the types of collisions. We just want them to be difficult to, well, have a low rate of collisions with whatever algorithm we're using. Yeah, very good. Yes, those are all desirable characteristics of hash functions. What are the two main types of acquisition? Yes. Live and static. So what's the differences between them? Yes. So a live acquisition, the system is still running, and you have to trust the system to give you the information. But in a static or a dead acquisition, it's turned off, and you don't have to have that same requirement of trust. Very good. What are the three main acquisition methods, and what do we get from them? Yes? Logical, sparse, and bitstream copy. Yes, very good. And what do we get from a logical acquisition? Yeah. 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 So if you're looking for a specific file or file type, then a logical acquisition would be the way to go. Very good. How about a sparse acquisition? Yeah.
Same as logical, but you also get some bits of allocated memory.
Bits of unallocated memory or data. Yes. So sectors from the hard drive, which we'll talk about today. I'm so excited. Yes. So what's the level of focus with a sparse acquisition? Yeah.
Partition or volume.
Yes. Very good. Yes. Yeah. Okay. And let's see. The last one is bitstream copy. What do we get from a bitstream copy? Yeah. Oh, come on, be a little more specific.
We're getting like a copy of all the bits from the drive.
All the bits, yes. All the bits. That's a little bit more detailed than all the things, right? We acquire all the things. Okay, very good. And what's the other name of a bitstream copy? Forensic copy. Very good. Thank you. All right. Why might we need to do a disk-to-disk bitstream copy? Why does that even exist? Yes.
There's something about the actual
Yeah, there's something about the hardware, the original piece of storage media that is important for some reason. Very good. What is the most universal evidence format? Most universal evidence format.
Isn't it like a raw?
Raw.
Image? Yeah.
Yep, raw. What distinguishes a raw image? Yeah.
It's the bitstream image file.
Yes.
And
Yeah. Yes. Yes. Yeah. So exactly. So we store all the ones and zeros, all the bits, right? It's just taken from here, and we're not doing any kind of compression or anything like that to make it more space efficient. We need exactly the same amount of space to store that bitstream copy in raw format as it was on the original device. Very good. What are some of the advantages to proprietary evidence formats? I just mentioned one of them. Yeah. Yes, compression. Very good. What else? Yeah. Integrate metadata. Why do we care about metadata? Say again?
It might be important to you.
So I think you're thinking of file system metadata. This is metadata on top of the data that we acquired from the evidence, okay? Why would we want that? Yeah,
Maybe like when you're investigating and you acquire the file, it might be something that you want to put in there as like a future note.
okay. How many of you have ever used a search engine? Of course, everybody has, right? Why does it return results so quickly? Is Google literally crawling the entire internet when you type in search terms? Oh, please tell me you know the answer to this. I'm not getting any like confident answers here. What?
Indexing,
Indexing, yes. What does that mean?
it means that you simplify it into a search structure.
Yes.
So that you can crawl it.
In other words, metadata, right? So Google pre-crawls the web for you, scrapes all the information that might be interesting to you, compiles an index of those terms by topic, at least that's how the original algorithm worked, and stores that. It doesn't search the entire internet, it searches the index. That's the kind of thing that is stored in the metadata in these proprietary formats. Can you see how that would be important if you're wanting to, if you have no idea what you're searching for, so you've done a bitstream copy rather than like a logical acquisition, and you're looking for keywords inside files or key like hexadecimal strings, right? You don't want to have to search the entire 4 terabytes of this guy's hard drive for that. You want it to be indexed, especially if there's lots of different terms that you want to search for, and you're not quite sure which terms or collection of terms is going to give you what you want, okay? So that's a really important feature of proprietary evidence formats. There's one more that I have here, which is that you can split the images. Well, they split themselves. So if you wanted to split a raw image, you could do that, but you would have to make sure to keep track of all the parts and put them back together properly. Proprietary formats take care of some of that for you, which is really nice. Okay. Last review question, then we'll talk about some awesome stuff today. Are you super stoked? I'm stoked. What does DD stand for?
Disk destroyer.
If I put this on the exam and that's your answer, you're getting it wrong.
Well, in the documentation, there isn't a name.
There isn't a name, it was a trick question, which means I won't put it on the exam, but maybe I will. No, just kidding. Very good. It doesn't actually stand for something. Some people call it data dump. Some people like to refer to it as the disk destroyer because you can do that really easily if you don't know what you're doing. All right. Let's get going on today's lecture. See, I don't need this anymore. All right. Okay, guys, so last time we finished all the process side of things, right? Forensics is divided into processes and deep technical knowledge, right? I keep emphasizing that over and over again. Today is the first day that we dive into technical stuff for the sake of doing forensics, okay? And since I don't know what you know, I'm gonna do some baselining here just to make sure that everybody knows some basics. So if you're like, this is really boring, I learned this 2 years ago, I'm just making sure everybody knows how to do some basic stuff, okay? So let's talk about base conversion, endianness, and just data structures at a very high level, okay? First, let's convert some numbers. Now, I don't know about you, but I kind of enjoyed learning how to do this kind of thing when I was in school, converting between different bases. So we have this decimal number. How do we determine its value? What's the value of 35812?
In dollars.
Yeah.
You assume it's in base 10, so
Yes.
you multiply each digit by the quarter.
Yes. Who? You got to say that louder though, because I couldn't say it better than you just did.
We assume it's in base 10, so we multiply each digit by the corresponding power of 10.
Right. Okay. So we draw this nice table, right, where we lay out each one of the digits of the number we're trying to find the value for. This might seem a little banal, but really, if we establish the pattern, it's easier in other bases, right? So we start at 10 to the power 0, which is always 1, right? 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4. And what we do in each of these columns is we say, all right, I'm going to take 2 times 10 to the 0, which is 1, 2 times 1, plus 1 times 10, plus 8 times 100, plus 5 times 1,000, plus 3 times 10,000. And that is how you compute the value of this number that, since it's in base 10, we normally wouldn't have to do that. But in other bases, that's the pattern for finding the value of a number given to us in another base. Okay. So let's practice with this binary number. How many bits do we have here? Binary digits. 8, right? So we're going to go from 2 to the power 0 to 2 to the power what? 7. Yes. So we've got our little table here from 0 to 7, and we go 1 times 2 to the 0, which is 1. 1 times 1. 1 times 2. 0 times 4. 0 times 8. Oh, sorry. Plus 0 times 4. 0 times 8. Plus 1 times 16. Plus 0 times 32. Plus 0 times 64. Plus 1 times 128. Of course, you don't have to do the zeros because they're 0. They don't affect anything. But I'm really hoping none of this is new to anybody. But if it is, do some practices, okay? Because we're not going to work a lot with binary numbers, but we are going to do a bunch with hexadecimal, okay? You're going to see a lot of hex. So if we were to do the same process for this hexadecimal number, 8BE4, or in the military, we like to say 8 beta echo 4, because you don't want to be ambiguous when you're talking over the radio and you want a lat long or you're saying something important, right? Okay, sorry. We're going to do the same procedure, right? How many hexadecimal digits do we have here? 4. So we're going to go from, or hexadecimal, so that's base 16. So we're going to go from 16 to the power 0 up to 16 power 3. Very good. So we're going to draw our table. Oh, first of all, by the way, B, the value of B is 11, and value of E, echo, is 14. So draw our table. We got 16 to the power 0 is 1, 16 to the power 1 is 16, 16 squared is 256, and 16 to the third power is 4096. So we go 4 times 1 plus 14 times 16 plus 11 times 256 plus 8 times 4096. And that will give us the decimal value of this hexadecimal number. Okay. Okay. Very similar, going from binary to hexadecimal and hexadecimal to binary. So the great thing about hexadecimal and binary is that they do really well together. So you've got every 4 bits will correspond to 1 hexadecimal digit. So you can just take them. If you've got 8 bits, you can just split it up into 4s. Take each one individually. So 1001. What is the value of 1001? 9. How do you remember? Well, you use your hands, right? Everybody know how to count to 31? Nobody ever taught you how to count to 31 on one hand? Everybody laughs when I get to 4, but it's 1, 2, 3, 4, 5, 6, 7, 8. Sorry, I've got disfigured feet. 8, 9, 10, 11, 12. Well, I lost track. Yeah, 13, 14, 15. Yeah, 16. So you get the idea. But I mean, I love counting in binary, right? So you got 101 is 5, right? And then you shift it over 1. See, is this clear what I'm doing, or? Because I like. Okay. So imagine my hand is each finger on my hand is 1 bit position, right? And if it's down, it's 0. If it's up, it's 1. So this is 1, and we put it down to get the next one. 1, 0 is 2, right? And then 3, 4, 5. So 5 is like this, and you shift it left 1, and then it's 10, right? And you shift it left again, it's 20, so, right? Now you have really dumb party tricks, right? For next time you're really drunk or something, and you're like, guess what? I kept 31 on one hand. Sorry. Okay. Okay. So we've got 9, and then what is 101? 100. 4. Right. So we got a 9 and a 4. Pretty easy, right? Not bad. We can do this. Okay. How about hexadecimal? Oh, and this using 9 times 16. Am I doing this right? So my brain does not, it refuses to calculate arithmetic. Like, you give me an algebra problem, I'll ace it, right? But arithmetic, just my brain refuses to do it correctly. So if I ever am doing some arithmetic up here and it's wrong, please just understand what I meant and not what I said. Okay. So, it's 148. Just let's move on. And then 9, we already established that, and then this is. You borrow a slide from somebody thinking they know binary. Man, that is not 8. That is 3. Anyway, the number, this hexadecimal number is 152. I apologize for the error, but I am throwing these slides together. Anyway, okay, let's move on. Okay, so talk data structures, okay? This is a really analog example just to get your mind wrapped around how we store information digitally. Not like you haven't thought of it before, hopefully, but okay. You go to get your Sun card, and they give you this little card, this little form to fill out. This is not how it's actually done, but let's just imagine this is how it's done, okay? And there's 2 spots for you to put information. Your name, which has 1, 2, 3, 4, 5, 6, 7, a bunch of fields, right? But fixed number of fields. And it's implied here, you can put 1 letter in each box, right? So if your name is longer than that, you're kind of out of luck. Your Sun card's not going to have your full name on there, right? And then your address can fill both of these boxes. Again, with the assumption that each box can contain 1 character or number. And if there's any spaces in there, you have to account for those as well, right? So I'm trying to think of any instance where you would actually have to fill out something kind of like this. Taxes, not like a little box. No. We used to have like Scantrons where you had to, the DMV. Yeah, okay. Yeah, all right, so you guys know what I'm talking about. Okay, moving on. So, with data structures, one of the big things we have to take into consideration is the size of data that we need to store in that structure, right? Makes sense, because if going back to our example, if we know for a fact that no one's ever going to have a name longer than, let's just say it's 20. I don't know if it's 20. I'm not going to take it. If we know that nobody's going to have a name longer than 20 characters, we're okay limiting that field to 20 characters, and we'll be okay. But we need to establish that in advance before we start printing off all these forms, right? Similarly, we have to be able to allocate a location on the storage device for whatever data we're going to put there. So a byte can hold only 256 values because a byte is 8 bits and 2 to the 8th is 256, okay? Again, I hope none of this is new, but we've got to make sure we don't have any gaps, right? So this is a byte is the smallest amount of data that we'll work with, right? Because it doesn't make sense to break those values any smaller because that's kind of the core base unit of computers. So if we're going to organize multiple byte values, meaning we have a value that needs more than one byte, we have to figure out how we're going to organize those. Now, when it comes to numbers, there's two different ways that we can organize numbers in multi-byte values. First is big endian and little endian. So endianness refers to the sequential order in which bytes are arranged into larger numerical values when stored in memory or when transmitted over digital links. So let's take some examples. Big endian ordering. It's most natural to start with big endian because we process numbers in big endian. Okay? So let's say we have this. So big endian puts the most significant byte of the number in the first storage byte. Oh, I don't have the examples until the next slide. Sorry. So let's talk. So there's a few different processor architectures that do use big endian ordering. And apparently there's like middle endian ordering too. I don't know why you'd come up with another endian scheme, but anyway. Okay, little endian ordering puts the least significant byte of the number in the first storage slot. I32 base systems, man, that was hard to say for some reason, use little endian. So here we go. So for an example, let's say we've got this hexadecimal number, 1, 2, 3, 4, 5, 6, 7, 8, which is 4 bytes that we want to store in memory. If we're using big endian ordering, what we've got here, so each of these blocks is a byte in memory, and these numbers across the top are the numbering or the address in memory where we're storing the information. So if we're storing 1, 2, 3, 4, 5, 6, 7, 8 in memory, we would just go in the first, for the first byte, we would store the 1 and the 2, the hexadecimal 1 and 2, the second 3, 4, 5, and then next 5, 6, and the final one 7, 8. That's what makes sense to us because when we look at that, that's how we process the information. But little endian ordering is actually different. So again, in memory, across the top is the memory locations. But you can see here that the most significant byte, meaning the leftmost here of the actual value, is at the end of the bytes. So we read this from right to left, 1, 2, 3, 4, 5, 6, 7, 8, like that. Okay. There will be times where you have to, I will ask you to translate something from little endian into decimal. It's also something that you're going to need to do for homework. So if this is something that is new to you, that you've never done before, again, this is something you're going to want to practice a little bit on your own, okay? Yes? That's just to show that this is not, that our memory does not consist of 4 bytes. It continues on either way. Any questions? Okay, hopefully we're filling any holes we have. Okay, what about strings? Does little endianness affect strings? Who says yes? Who says no? Oh, there's actually fewer no's. That's interesting, because the right answer is no. So it doesn't, because endianness only affects numerical values. Here's why. The most common techniques to encode characters are actually to use ASCII and Unicode, not the actual number value, which means, so just some background. ASCII in hexadecimal goes from 00 through 7 franc. Yes, that's 7F, sorry. Including control characters, we've got 1 byte per character, and that's really what it boils down to. Is that we're not, for ASCII, we don't use more than 1 byte for a character. So the Indian ordering doesn't play a role since each byte stores the value of the character. A lot of times strings end with a null character or 0, 0. Okay, so ASCII. Just focus on ASCII for a second. This is the example. I don't think that. Oh, there we go. Okay, sorry, I didn't realize that animation was there. Okay, so if these are our memory locations across the top, and the bottom is we're filling in the values of the DMV, right? We've got 1 space MAIN space ST period, and then the null character to end our string. These are the hexadecimal values here in the middle that ASCII will translate into when it gets stored into memory. You can see 31, 20, 4D, et cetera, et cetera, et cetera. And then because the computer knows that ASCII text, it will just take it 1 byte at a time. Any questions? Yeah.
What about like Unicode? Some of the other.
Let's talk about Unicode. Okay, so Unicode is really interesting. Apparently, version 11 was just released last June and contains over 137,000 characters. I don't know if you've ever looked into Unicode, but it's fascinating just how organized and structured it is. You can tell that it was definitely an international collaborative effort to standardize Unicode. Anyway, sorry, a little aside, but it covers over 146 modern and historic scripts as well as symbol sets and emoji. So if your phone doesn't support a particular emoji, it just means that it doesn't have a particular font. That's what it really boils down to. It's not this version of an emoji and that version of emoji are a different character. It's a different font. Sorry, that's a little pet peeve I have. Yeah.
Wait, so, like, you know how you get the box, right?
Tofu. The tofu.
That doesn't sound like.
Yeah. So some people call it. Yeah.
Okay. Doesn't that usually mean that dated or like it's not updated to the latest version? Or is
Maybe.
it
So
could it be like either or?
yeah. So let's not get into the details, but it's possible. Anyway. Okay. Unicode. 4 bytes per character. That's what Unicode takes. Anybody see a problem with that?
Not enough space.
What do you mean not enough space?
Have every character of everything, every language. Every symbol.
Yeah, sure it does. Right now, version 11 supports 137,000. Well, there's still lots of empty blocks of Unicode addresses that, like 9 whole blocks that they haven't filled. Anyway, what's the problem with using 4 bytes per character? Yeah.
Indianness.
Yeah. What's up?
It's really big.
It's really big. How much bigger? 4 times bigger than ASCII. 4 times. Can you imagine all of your files on your computer suddenly taking up 4 times as much space on your hard drive? That's a lot, right? Well, do we always need all 4 bytes? So here's the thing. There were a few methods that were contrived to represent Unicode, and the first was UTF-32, and it uses 4 byte values for each character, always standard, never changes. You don't have to do any like figuring out if there's going to be 4 bytes or not, right? UTF-16 then came out, and they're like, you know what, we can do better because ASCII covered a lot of characters that are in use, and for those, I mean, we can cut it down. We can have some mechanism by which we decide whether or not we need to use 2 bytes or 4 bytes. And so they came up with UTF-16, which means that every character will use at least 2 bytes, except for the ones that need more than 3 bytes because of the leading zeros, or lack of leading zeros. And then they'll use 4 bytes, okay? But then people came up with UTF-8 and they're like, whoa, 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 whoa. UTF-16 is just, it's still a gigantic waste of space. We can do even better and use only 1 byte for all of the ASCII characters, and anything beyond that will use either 2 or 4 bytes, depending on where it falls in the range of values for the 4 bytes. Okay, so kind of cool. UTF-8 is awesome, and every now and then I'm doing something in Windows, and I'm like, oh man, if only everything was UTF-8, right? Because it's so much, the encoding and decoding is an issue with other, because there's so UTF-8, 16, 32, those are not the only ways to encode text data into bits. There are others. Anyway, okay, I'm getting off on another tangent. I need like someone with a sign that says you're off on a tangent, stop, or something. Okay. So different methods make different trade-offs between processing overhead and usability. So what I mean by that is UTF-8, what you've got to do is read in that first byte and decide whether or not you need to read in more bytes. So that's the processing time that is a trade-off for being more space efficient, because with UTF-32, you always know that you're going to read in 4 bytes, so you don't have any processing overhead. Okay. Okay, data structures. And to answer your question, which I tried to dance around, I'm not 100% sure, but I'm pretty sure that endianness does not affect UTF. But I could be wrong. Anyway, bottom line, any of the text that you are analyzing for this class will probably be ASCII, which is the first block of UTF-8 anyway. All right, data structures. Data structures describe the layout of data that is broken up into fields, and then each field has a size and a name. That's what a data structure is. We're going to say, all right, we're going to put this information in this order. This part is called this, and it's this big, et cetera, et cetera, et cetera. That's a data structure. So when you're doing a write operation on a data structure, here are the things that you need to be aware of and make sure you account for. We've got to refer to the appropriate data structure to determine where each value should be written. Meaning, if you've got this value here, you don't want to put it somewhere else in the data structure where it doesn't belong. That's just something you have to be careful of. And then the read operation, you need to determine where the data starts, where's the beginning of the data structure, and then what's the offset from the start that the value begins, or where you should start reading. Okay, again, I know this is all like very fundamental, but I don't want there to be any holes in understanding, gaps in understanding. So let's do an example. I give to you this awesome data structure, which comprises 32 bytes, sorry. Whew. 32 bytes. The first 2 bytes are an integer in little endian, and the next 30 bytes are ASCII, and they represent a street name. So the first 2 bytes are house number, the rest of it is a string, and it's a street name. So here's what we're viewing here, in case you've never seen a hex editor before. These are the hex values in memory, starting at address 0 for 2 entries that use this data structure. So we know that it's 32 bytes, so this is the byte offset in hexadecimal, which means right here is 32. So these first 2 lines are 1 entry, and the first 4 hexadecimal digits are what represent the house number, because that's 2 bytes. So we can see over here that these decode to just a period. So hex editors, by convention, if they don't know how to decode a byte, or it doesn't decode to a valid ASCII character, they'll just put a dot so that you know that it's something but not within a printable character range. Okay. So we got ... which is the two bytes at the beginning, the two integers bytes, and then main street period. That's 2E is a period, and then null character for the rest of the data structure. So what is the house number? I'm hearing a 1, I'm hearing a 2. Anybody gonna, what's that?
Is it big endian or little endian?
That is the question, yeah. I actually did say earlier that it's little endian, so that does matter. You want to say 4? You want to say 4? No, it's not 4. Because it's hexadecimal, first of all, so it wouldn't be 4. It'd be 4 if it was just binary, right? No, it wouldn't. But what's the house number? 1. Correct answer is 1. So when you're converting from little endian, sometimes it's hard. Like, you know that you have to reverse stuff, but you're not quite sure where the boundary is. And you might be tempted to translate this into 0010, but you got to take two hexadecimal digits equal 1 byte. So you take 1 byte, put it at the beginning, and then you got 0001. Okay. 2 hexadecimal digits equals 1 byte. Okay. Okay. Data structure is important. That's the main takeaway. Who's ready to start into something else? Okay. We'll start in 2 minutes. We're going to take a little break.
So if you crack the top of it, if you crack the counters, it's big, and if you crack the vanilla, and if you crack the little part, sorry, the big part, that's big. And yeah, if you like smack it, origin, smack on the right here, on the larger end.
I was wondering if you put the QR code back on the screen. Oh, there we go.
Having trouble?
A little bit. There we go.
So it's like stored. It's like each group
Got it?
of like 4
Yeah.
bytes.
Okay.
Thank you.
So
Yep.
each grouping of 2 bytes is a little endian. The whole thing is a big.
Okay, let's start again. So today we're going to talk about hard drive geometry, but before we get to that, I need to talk about one more kind of abstract topic, just so that you can better appreciate why we're doing things in a particular order. Okay, because talking about the layers of forensic analysis helps you understand. It's going to kind of decompose some of our thought process that's really natural. If I were to give you a hard drive and tell you to find me a file, you would automatically know how to do a certain number of things without even thinking about it. What we're going to do is kind of deconstruct that and say, okay, what are you actually doing when you're making all these assumptions or going through these steps? Okay, so I think that's helpful in the context of forensics to make sure you are aware of the steps that you're taking, not only so that you know the proper way to do it, but so that if you were going to automate it in a program, you have already done that process, right? Because really, writing a program is just decomposing decisions into smaller and smaller pieces. So, layers of forensic analysis. Am I not focused? Okay. So, when we start with evidence, generally it'll fall into kind of 2 different categories generally. This is kind of an old model, but anyway, so we got network analysis and storage media analysis. Network analysis we're not going to pay attention to right now. That's kind of its own direction. We're not going to settle on that one. So storage media analysis are kind of 2 different directions you can go from there. The first is memory analysis, which again is kind of its own thing and has different structures and that are operating system dependent and all that. So the other direction is volume analysis. And volume analysis, there's kind of 3 parts to it, depending on what's in the volume. And we're going to have to define very clearly what a volume is in just a second. But from the volume analysis, you either have a file system, a swap space, or a database. Those are kind of the 3 main options for what is in a volume. So, from the file system, that is where you can start to pull out files, obviously, and take a look to do application and operating system analysis. Okay, so let's kind of make this a little bit more concrete, less abstract. If you have a hard disk, you're going to first do storage media analysis. The output of doing storage media analysis is you will find sectors of data. And you'll know their layout, their construction, their size, where to find them, all of that. From the sectors of data, you'll be able to do volume analysis and discover where the volumes are on the storage media. And then by analyzing the volume, doing some file system analysis, that is where you will actually be able to discover files themselves. Okay? So we're going to talk about storage media analysis, volume analysis, and file system analysis separately and in that order, okay? Because we kind of got to build it up. So, any questions so far? What is this? What's that? No. All right. We kind of just went through this, so I'll click through it pretty quickly. Storage media analysis, specifically non-volatile storage such as hard disks and flash cards, organized into partitions and volumes. Partitions and volumes are, well, yeah, they're storage locations that a user can or an application can write to and read from. That's just a high-level definition of partitions and volumes, even though they're kind of separate. The contents of partitions and volumes are file system and database or temporary swap space. If you're not familiar with swap space, we might talk about it later, probably when we talk about file systems. Okay, volume analysis. What we're doing is we're analyzing the data at the volume level. what kind of acquisition focuses at the volume level? That we talked about earlier today. Yeah.
Sparse.
Sparse. Yes. Very good. Kind of reconnect those dots, right? Because we got interdependencies here. Okay. With volume analysis, what we're trying to accomplish is to determine where the file system or the other data that's inside that is located. And we also determine where we might find hidden data, which is, of course, a critical piece of information. Okay, file system analysis. What we do in file system analysis is, file system is a collection of data structures that allow an application to read, write, and write files, create, read, and write files. The purpose of file system analysis is to find files, recover deleted files, find hidden data. The result could be file content, fragments, metadata. That's what you get from doing file system analysis. Okay. Application layer analysis that wasn't in our earlier diagram, kind of was down at the bottom left-hand corner. Here what we're doing is we're looking, the structure of each file is based on the application OS that created the file. So a lot of times, if you're given a particular kind of file, you can know just from the kind of file it is what operating system created it. And that's what we're talking about here. So the purpose of doing application layer analysis is not only to analyze the files, but to know what tools we need to actually do the analysis. Okay, just as a reminder, this is our flow. We're going to go from storage media analysis, volume analysis, to file system analysis. Here we go, guys. Oh, I've been waiting all semester to get into hard drive geometry because I think it's fun. And if you don't know very much about hard drives, you're going to, okay? I've got so this is a Chromebook, right? I've got Android apps on it. I've got like an Android app all fired up to like draw pictures for you with my finger and everything. I'm excited. Okay. Hard disk geometry. Here are some key terms for understanding hard disk geometry. First is the head. This is the device that actually reads and writes the data to the drive. It's responsible for making the data persist and then retrieving it later. A track is a concentric circle on a disk platter. I've got illustrations, don't you worry. Cylinder is a column of tracks on disk platters, and a sector is a section on a track. Let's use some pictures, yeah? So, the most important part of a hard drive is the, actually, I don't know if it's, the head and the disk platter together are the most important, right? So the disk platter is where everything is stored, and the head is what just does the reading and the writing. And the head bone's connected to the head arm, and the head arm's connected to the actuator, right? So, and the actuator is connected to the chassis. Okay, so these are if we were to rip apart a hard drive, this is what we would see inside, and these are the major physical components of the hard drive, and their names. Okay, I almost broke out into song, almost. Okay, so here's another illustration. If you were looking down from above to the disk platter, we could draw these lines that designate different areas of the platter. So the first platters are divided into concentric rings called tracks. So okay, sorry. I don't know if this will work very well, but all of these circles right here, I'm doing this for the sake of people watching this on YouTube. All of these circles, each one of those is called a track. So if you forget what a track is, just think, well, if I go running at the track, there's all these little lines and they go around, and if I come back around, I'm in the same place. I'm not in a different track, right? Not like a record, not like a track on a record. You all know about records, right? You put the head down and it spins around and it slowly gets closer to the center. Okay, not the case with these tracks. Okay, These tracks are just like a running track where you go around, you don't leave the track, you're going to be in the same spot where you began, okay? That's a track. Labeled A, that red circle. Tracks are divided into wedge-shaped areas called sectors. Sectors are super critical for understanding forensics, okay? We talk about sectors all the time. This is the basic unit of storage on a hard disk, okay? And it's labeled C, meaning not the, so this says it's wedge-shaped, but it's not the full purple area. That's letter B that, well, okay, so a sector typically holds 512 bytes of data. This is like, okay, but not always. But for the most part, 512 is like the industry standard. A collection of sectors is called a cluster. In other words, letter D, that green space down at the bottom. And then B is something called a geometrical sector. That's not a term that you see like ever. So you don't need to remember that. But I didn't want you to be confused why I didn't use all the labels that I pulled from Wikipedia. So that's why that's there. Questions? Good. All right, so cylinder. A cylinder is a vertical collection of tracks, okay? So if you're looking from the hard drive from above, if you look at one track, everything below it is, all of them together is called a cylinder. Cylinder is super important for understanding what we're about to talk about. So if there are any questions, or if you need me to explain that in a different way, or draw a picture, I'm ready, okay? What is a cylinder? You tell me. What is a cylinder? Yeah.
All of the tracks that are on top of each other.
Oh. Yes, good. Now use your words. Yes, good. Yes, use your words.
It's kind of like those baby for
No, because they're different sizes. So that analogy doesn't work. I'm so sorry. Thank you for trying. Please play again. Someone else, use your words for what a cylinder is. I want this to be in your head. I want you to have to think twice about what a cylinder is in a second. One more person. Yes?
It's a track stack.
Track stack. Yes, I love it. We're going to end on that one. Okay, so a cylinder is a three-dimensional concept consisting of all tracks in the same position vertically. Okay, going back here. Everybody know what a head, arm, actuator, and chassis are, okay? Very good. Time for a drawing, okay? Because I'm going to explain a couple things to you. But to do that, I've got to do this. I'm just going to screw everything up, but that's okay. Let's just do blank. Come on. Don't let me down now. Okay. So I'm going to draw some circles here. All right. So we've got a hard disk, and we've got lots of platters on it, right? So the track goes around in a circle like this, right? Well, here's the thing. Actually, let me draw it this way. If we're looking down on a disk platter, and we've got our track that goes all the way around, and we end up in the same spot, right? Here's a critical piece to understand. Well, first you got the little shaft that the platter spins around on. All right. Now the head kind of sticks out like that, right? The head it moves around on an actuator, so it can only move two directions. It can move in and out. That's it. It goes this way, right? What happens is the platter is spinning around and around, and the head just waits until the platter is in the position on the track that it's on to grab or write the data that is queued up. So 7,000 RPM. revolutions per minute. And then there was this big like, oh dude, I got 10K hard drive, right? That it could spin, the platter is spinning so fast that you don't have to wait very long for the platter to get in the position that it's supposed to read your data, which meant that your operating system booted up fast. It was the SSDs of 10 years ago, right? Oof. Yeah. So okay. So the head moves back and forth, and so the tracks are numbered from the bottom up. I think I have that in a slide in a minute, but the number from the bottom up, and that's the first set of data on the very outer edge of the disk. That outermost track, that is where data is written to first on a platter. Why? Knowing what you know about how platters are organized, why? Yes, so when that's part of it. So when the head is at rest, meaning it's not reading or writing, it'll flip to the right in this picture and just rest so that if it gets bumped or whatever, the heads won't scratch the platters. But there's another reason. Yes?
Where the most surface area is, you can hold the most data on the outside part as well as it's getting the fastest because it's the radial speed, the further distance you get out, the faster it is.
Yes, very good. So he said two critical things. First of all, because the circumference is greater on that track, you can actually have more sectors along the edge, and it's moving faster, and it's closer to where the head is at rest. All of these reasons mean that you want to fill up that first track first. You want to fill the outermost tracks first for the sake of speed, reading and writing. It doesn't matter, right? It's faster the further out on the tracks that it is. Okay? So we're going to fill up all that whole first cylinder. We're going to fill up with some caveats that we'll talk about later. That whole first cylinder, we're going to fill that up first and then move towards the center. You've got to have that mental picture in your mind for addressing of all these sectors that we're going to talk about in a minute. Any questions about this though? Yes.
Your line to get.
Oh, that's right. Hi YouTube. Dang, that's like really embarrassing. That's okay. Here, we're just gonna take this off. You live streaming in class. Look at you. That's fine. Okay. So I feel really bad for all those people on YouTube that had to look at my ugly face, right? Man. So I am gonna screenshot that and insert it into the notes right here, okay? So that you can reference it. If it helps, if it doesn't, just ignore it. But if it does, I want you to have access to it, okay? All right. Yes, please.
So if we have information, let's say we got a movie story on our sector, it's going to want to try keeping that movie in the same sector. Yes. So as it's spinning, it's only going to hit that sector once per rotation. So does it like know when to read that and then stop and then when to pick up again?
Yes, it does.
That's kind of cool.
Yeah.
So then what if we have multiple things going at the same time? Does it like know when to like pick up and change the content?
Of course, yeah.
I guess obviously because that's how it works. It's just a weird concept.
Yeah, so your hard drive has a little bit of a buffer, right? So you send it commands, hey, I want you to read in the data from this sector to this sector, send them to me. Oh, and by the way, write this out, and like it's in this queue, right? And so there are lots of techniques for optimizing that, for making it so that if there's some kind of problem, it doesn't like destroy the data that's on there. There's lots. It's a whole like research area. So, but yeah. Any other questions about hard disks? We're actually not done talking, but Yes.
How does it keep track of coder?
Oh, dude, that's like at the hardware level. I would always CS. I would never CSE. So if you want to talk to CSE to somebody else, you get on. But I don't know the answer to that. But yeah, I don't know. I know there's a motor and there's an actuator, and they do their thing. I get my data. That's all I care about. Any other questions? Okay, so we're going to talk about how each of the sectors on a hard disk are addressed. Actually, to be more accurate, how they used to be addressed, because this addressing method no longer is really used, and we'll talk about why. So, CHS. Anybody want to guess what CHS stands for?
Cylinder head sector.
Yes, cylinder head sector. Very good. So, again, so just to reiterate to make sure we don't have any knowledge gaps. Tracks and cylinders are numbered from the outside in, starting at 0. That's the piece of information you didn't have before, right? Starting at 0. All sectors of the tracks in cylinder 0 will be filled up before using cylinder 1. Not actually 100% correct, but we'll talk about why later. Heads numbered from the bottom up, starting at 0. All platters are double-sided, so there's one head per side. So if we go back to our lovely drawing here, you can see that there's, in this image of a hard disk, there's 3 platters, but there's 6 heads because there's a head for each side. Now, on this, the image on the right, you can see that the heads in between platters have one on each side. So there's like a minimum clearance distance for those heads to be able to actuate in between those platters safely. Okay. Finally, sectors. Each sector is numbered starting at 1. Who came up with this? I don't know, but it's a thing, and this is the numbering scheme for CHS addresses. Okay. So the very first sector, I'm going to emphasize this over and over again so that you don't have to look it up when someone says, how much data does a sector hold? You can just say,
Sometimes 512 bytes.
512, yes. Sometimes 512 bytes, yes. No, that's like the standard answer. 512 bytes. How much does a sector hold? 512 bytes, half a kilobyte. I don't care how you have to think about it. Yeah.
So if you take like a terabyte and divide it by
So,
well, like after converting.
what you would actually do is look on the label, and it will tell you the sector size. So for drives that big, usually what they do is they make the sectors a little bit bigger, like 4096, usually. Yeah. But historically, and for the purposes of this class, sectors are 512. Okay. Okay. First sector has a CHS address of 001, and this is how you write it: with a 0, 0, 1. Any questions about CHS? Okay. Now we're going to talk about logical block address. So what happened was that CHS has a limit of 8.1 gigabytes. That's not very much, even for 15 years ago. Not very much storage. So they had to do was say, you know what? We're storing the CHS address in kind of 3 different areas in our data structure where we store that. That's inefficient. Let's just store a number. Like, let's just address them starting at, anybody want to guess?
0, 1.
Man, yeah, 0, there it is. Starting at 0. So a couple of these are the points I clicked through. Yeah, we can talk about that. All right, so we have single address instead of 3. Talk about that. Start at 0. So LBA 0 is equal to CHS 001. All right. So to convert from CHS to LBA, what are some things that you need to know? Yes,
Sectors per platter.
you got to be more specific than that because there's lots. Yeah, you got to be more specific. Because platter is not one dimensional.
How many sectors are on each track?
Sectors per track. Yes. What else do you need to know? Yes.
How many cylinders there are? Not how many, yeah. How many platters there are?
Yes. How many platters there are? Yes. Why? Why do you need to know that?
So, again, one of those numbers is related to the platter.
Which one? Come on.
H.
H. Why?
Stands for something specific.
Head. Right. So what's the first head? Where's the first head? It's on the bottom, right? And what's the number? 0. So head 0 is down at the bottom. That's the first one. How do we know when we need to switch to head 2 or 3 or 1? We need to know how many sectors per track, per cylinder, same thing, and the number of heads so that we know when to go into the next cylinder, into the next track, okay? All right, so CHS address, obviously, because you've got to have something to convert from. That's kind of a given. The number of heads per cylinder and the number of sectors per track. Those are the 2 additional pieces of information that you have to do the conversion. So, yes, go ahead.
What about a track with like circles?
Yes, yes.
Or how do you get sectors?
Okay, so it's going to be defined by the manufacturer of the hard disk. They'll say this is how many sectors are in each track. So if you look,
Oh, no, yeah, no, I was thinking about it.
yeah, no, it's fine. So this illustration shows that there are the same number of sectors on the innermost track as the outermost track. And that's actually not accurate, right? That would be a complete waste of space to have the same number of sectors on the innermost track as the outermost track, because there's so much surface area. We were just talking about that. There's so much more area on the outermost track. Why would we not use it, right? Yes.
So if there's more space, how would you split it?
It depends on
Like, would it just be like-
the manufacturer. So, but ultimately, you're going to have some tracks that have more sectors, and innermost tracks are going to have fewer, right? So there's going to be some documentation of that. Yes.
Why don't we just do the number of-
You do, but knowing all the number of all, because you just start from the outside in. Yeah. If you wanted to compute the number of total sectors on a hard drive, you would need to know that. But if you already have a CHS address, knowing the endpoint doesn't help you get in the middle. Does that make sense? Okay. All right, this is a good enough space or spot to stop for today. We're going to talk more about CHS conversion next week. Have a great weekend. We'll see you next time.